Hello, everybody. I'm very happy to be here again on this conference. The first year I'm going to this conference, and I'm not in Russia. I really regret that, but it's what it takes. So thank you for being here attending this talk. The goal of this talk is to basically take a very wide and open view on how to take Postgres, the Postgres that we all know and use every day, and see if we can rethink it, and actually I'll explain why we constructed it into a platform that may run natively in cloud environments, or particularly what's called cloud native, which typically refers to Kubernetes and its ecosystem. So the path we're gonna follow today is basically how to take this Postgres, again, that we all know, some people call it a monolith, but definitely it's a piece with a lot of integrated components, and see if we can take some of these components out and offload functionality to well-known software on the cloud native ecosystem, such as Kubernetes ecosystem, and run it on a different way. Rethink how Postgres is deployed, how Postgres is automated, and how Postgres integrates with all the components to make it a more cloud native experience. I will explain what does it mean. I'll not get into the buzzwords. This is not about trying to make things hype or overhyped, but a reality on how to really take a very old, but at the same time, of course, new and powerful technology, Postgres, into the Kubernetes ecosystem and cloud native ecosystem. So bear with me. We're gonna have this session split into two. There will be a presentation part at the beginning, starting right now. Then we'll take a short break before a Q&A session. We'll have a Q&A session, then we'll take a short break just to freshen our minds, and then we'll go into a hands-on lab session. I'll run that hands-on lab session, but you're more than welcome to also try this at home or at the office or wherever you are. The only thing that you need is a Kubernetes cluster. I'll also explain how to create one on the cloud if that's not, just in case. But if you have a Kubernetes cluster next to you or handy, get it prepared, because in the second half of this presentation, you're going to be able to exercise everything we're going to be explaining today on your own Kubernetes cluster. So before starting, compulsory slide about myself, or the who am I? I am the founder and CEO of a company called Postgres. Postgres means on Postgres, so it's pretty easy to understand what we do. We're specialized on Postgres, right? I've been myself for more than 20 years a Postgres user and Postgres DBA, application developer in Postgres. Like I've worn all the hats related to Postgres world, and I love to basically belong to the field of R&D, research and development, trying to come up with new ideas, new technologies to empower the Postgres world. I'm actually quite frequent speaker. This is, I don't know, my nth talk at PGConf Russia, and many other database conferences, also some programming conferences. Some past projects that I've created in the past or architected, lead, like ToroDB, for example, software, open source software that we developed to replicate real time from MongoDB to Postgres while transforming JSON documents on the fly to relational data structures. And I also like to do a lot of community work. I founded a nonprofit in Spain, but with international aim, called Fundación PostgreSQL, a nonprofit dedicated to Postgres. And well, I tend to have experience in the cloud. I've got this recognition called Amazon Data Hero, but I like all environments, all cloud environments, and I work all around the place. If you want to find me, I can be found on Twitter, on my email, but also all my references, public references, are on my website, aht.es. You'll find on the bottom right on the screen. Feel free to check it out. All my talks eventually also end up being there. This one will not be an exception. So ping me on Twitter, email, LinkedIn, website, no problem. All right. So before diving into how we can deconstruct Postgres, let's look at what I call the stack problem. So let's look at, if we take Postgres and we look at containers. Containers, are a convenient way to pack functionality of a given software and gives us an uniform comparison point. And let's look just at the beginning to start with at the size of a container. And let's compare Postgres containers with Oracle containers. This might not be a fair comparison, but bear with me. So if we take Postgres container, the official Postgres image by default, it's around 300, 400 megabytes. There's even a simplified or reduced version, which is based on Alpine Linux instead of Debian Linux, which is even less than 100 megabytes. So we could say that Postgres database, it's actually quite small. Source code of latest, not the latest, prior version, just as an example here, Postgres 12, source code is just 19 megabytes, of course compressed, but then compiled Postgres, all the binaries are actually no more than this size, around 20, 30 megabytes, all these binaries, and you don't even need all of them to just run the Postgres database. It could be actually possible to create a Postgres container with just the very few binaries and libraries, shared libraries and small some configuration files on a kind of a distroless container that will be able to run Postgres perfectly well, ready for production environments in probably around 20, 30 megabytes, maybe slightly more. But this is the order of magnitude we're talking about, either less than 100 for like strictly strongly optimized containers, or a few hundred megabytes for containers including full-blown distributions. So I would say it's a pretty lightweight given all the functionality that comes with Postgres. Now, if we look in Oracle container for version 12, for example, it is 3.5 gigabytes in size. Wow, this is 10 times more, one order of magnitude more than Postgres worst case scenario. So why is this? Why Oracle container is so much bigger than Postgres? Is that Oracle is so much better? Well, definitely not, and I'm not going to get into that fight right now. It just comes with more things, which obviously makes up for this size, right? So if we look at this, Postgres in reality is just a kernel, right? When you run Linux, you boot a kernel, which takes care of the operating system and devices and exposes an API, the system calls, but then you need tools on top of that. It's typically the GNU ecosystem, right? All the tools that we know, the shell, the grep, awk, ls, and all these binaries and shared libraries that we have, that typically goes together. You normally don't use just the kernel itself, right? So Postgres is not so much different from this. You just typically don't run Postgres itself in production. You need to bring together with Postgres a set of tools that you will use in production environments to provide functionality such as backups, connection pooling, monitoring, etc. We're going to talk about this. So we tend to think of Postgres more as a distribution, that what you need is a distribution of components, including Postgres plus some others, in order to deploy production workloads. So it can kind of require a red hat of Postgres to really run Postgres in production. Now, where do we find all these tools? In the Postgres ecosystem. Most of them don't come with Postgres itself. Postgres relies on the ecosystem, where you may find typically it's open source, but there's also proprietary tools, and you'll find everything, practically everything that you need for this enterprise stacks, enterprise workloads needs, all the tools that you may need. Now, the ecosystem, it's a little bit like Dr. Jekyll and Hyde, Mr. Hyde, because there's good things about this, and there's also not good things about this. The good thing is that there's a lot of variety. You can pick any tool that you want from the ecosystem, and there's a wide variety of tools for almost any functionality you want to cover, and so you're well covered. And the bad thing is that there is a lot of variety, exactly the same thing, because there's a lot of variety, you need to pick, and picking is not easy, especially if you're not a Postgres expert and you're not well into Postgres. Which of these 3-4 connection poolers should I use? And how should I configure it to interact perfectly with all the components that I have selected? So it's good for Postgres experts, might not be that good for non-Postgres experts. And one of my goals definitely is to bring Postgres to many more people than it is right now, including non-Postgres experts. So what are those components? These components that I'm referring to all the time that should compose what I call this Postgres stack, what should be an enterprise-grade stack, which is what you need to run Postgres in production. There are several of them. Let me briefly describe them. First of all, we should talk about optimizing the configuration. Postgres configuration by default is quite bare bones, it's quite conservative, and we really need to tune this configuration, right? There are several resources that you may use for this. There's not like a lot of downloadable tools you may put into the stack, but at least there's some online resources. There's one that actually we created in our company called PostgreSQL co.nf. So it's like PostgreSQL.com file, except shifting the dot 2 places to the right. It is a quite handy free online resource containing both documentation about all Postgres parameters in all versions and translated to 5 or 6 languages. But it also contains a new functionality recently launched where you can just upload your PostgreSQL.com file and have it tuned, getting a tuning guide with recommendations there, store your files there like if it was like your GitHub or repository of PostgreSQL.com files. And you can also download in several formats or use an API to gather these files and include them in your Ansible or deployment scripts or whatever you want. So this is the first step, to configure, to tune the optimized Postgres configuration and being able to have an optimized configuration, which you may leverage some tools that exist. Then it goes connection pooling. It's well known that Postgres needs to be deployed with connection pooling. There's very few use cases where you shouldn't deploy Postgres with connection pooling. I'll not get into the details. This is a really long topic and conversation, but basically this graph that is shown in the screen shows that Postgres on a small server, in this case, just to show as an example, may struggle, may do well with if you throw in a lot of connections, concurrent connections, in terms of TPS transactions per second, but latency will spike to unacceptable levels. And the way to solve this is by using a connection pooler. So you typically want to use a connection pooler with Postgres. Now, which one? If you look at the ecosystem, there's pgpool, there's pgbouncer, Odyssey, pgagrol, which was a new addition. So which one do we pick? Which one is the best one? Or which one is the best one given my needs? And by the way, where do I place the connection pool? Should I place the connection pool just fronting Postgres next to it, or as a middleware layer, or on the client side, or a combination of those three, or in the 3 places, all of them? And which connection pool in which location of this architecture? It's not easy, right? So there's a lot of questions to provide there, and also to fine-tune and configure the connection pooler itself. So this is what I was referring to, this ecosystem problem. There's a lot of variety, there's tools to choose, there's tools to configure, to fine-tune, and then to make them all operate together. And this is definitely not an easy problem. But then we'll talk about high availability, right? The same problem appears. There's several tools to pick from. There is a pgpool, rep manager, Patroni, pg autofailover, PAF, stolen, and even other considerations for high availability, right? Which one to pick? Which one is the best? Some of these tools may cause some problems actually in your cluster. Pick wisely, right? The same applies with backups. Which tools should I use? There are several you can see on the slide, right? And where do I do backups, right? Do I do backups to cloud storage, to disk? And what about PG dumps? No, that's not backups. It's logical snapshots of data done. That will not back up your database for production environment, unless it's also on top of any of these tools that do continuous archiving. So you also need a tool for backing up Postgres, and there are several alternatives. Again, there's a problem to choose. Where should they go? There's an aspect that is often overlooked into enterprise Postgres deployment stacks, which is the logs. Normally, the logs just happen to go on the file system, and that's it, right? But what happens if you need to troubleshoot an issue that happened on one server, but also there was running on another server, it was replicated, and you need to start, or you don't even know on which server it was. So then you go to SSH to each server, cd to the logs directory, do a grab there or awk or whatever you're going to use to find the specific log that you're looking for, and then you realize that was not the server, so you SSH to the other one, rinse and repeat. It's very complicated, and that's why we believe that an enterprise-grade Postgres stack should have the logs all sent to a centralized location where I can parse or query all those logs together at the same time. I don't need to go to each and one of these servers, which would also require their own storage for the logs and rotation policies, and actually complicated systems to store all the logs. There are some tools that are not specialized for Postgres that you may use, like the ELK stack, which will bring a whole lot of new dependencies. It's a quite complicated stack technologically from a technology perspective. But there's no significantly specific technology for Postgres except the one I'm going to present today. There's also the entry point problem. Whenever you have a Postgres cluster, you may have a primary node and replicas. But if this primary node dies, the high availability software is going to promote one of the other replicas. But how do the applications know where the primary is all the time? How do we avoid changing the applications? This is called the entry point problem. And you can solve it in several ways, including DNS, virtual IPs, or all the mechanisms. But basically, you need to have from the application as standardized and stable entry point to the application. Now, one thing that we can do, and it's not very usual, but it's starting to get more popular, is to use a proxy to serve as the entry point to Postgres. In particular, I'll show you and explain you later why we're using Envoy proxy with a filter that we have developed for Postgres to enhance the experience of using Postgres through this proxy and what benefits it will include. I'll show you. I'll talk about this later. What I'm going to say about monitoring Postgres for enterprise-grade workloads is absolutely critical. Here we have so many tools, I'm not even going to mention them. Prometheus may be one of the most used right now, but it's by far the only one. And we need to understand which tool to use, how to configure, how to monitor, and even how to not overwhelm Postgres with too many queries just from the monitoring perspective, which can happen. So it's also, again, another component of this stack that we need to consider. And last but not least, and it's the user interface or a web user interface. There's not a lot of tools for managing Postgres clusters. There's tools for accessing Postgres and running DDL commands, doing queries, but not for managing clusters. And I am a command line person, don't get me wrong, but there is a lot of people, a lot of users who are more comfortable with user interfaces. And it's great to have some kind of web interface to manage all your Postgres clusters. So this is what I call the stack problem. We need all these components which are external to Postgres. They don't come with Postgres, the official distribution, right? To run a Postgres enterprise workload. And then where are we going to run this? So we can deploy the stack into many environments, like cloud environments, like on-prem, right? So how do we actually take all these components, program all these components together, make them work together well, and ideally automate all these to work on any environment? Sounds like a quite complicated problem. Practically, the answer to this, the only answer as of today to this, practically speaking, is Kubernetes. Kubernetes offers us a programmable API against which we can program the deployment of all these components and make them all together. And that is basically what I'm going to be talking about today. We've built a software called Postgres, which, as you can imagine, includes a stack. This is a stack of components on top of Postgres, hence the name Postgres, a set of stack components on top of Postgres. And it enables to run Postgres with all these components that I've mentioned before on Kubernetes, on a cloud-native platform, right? And in doing so, and thanks to this programmability of the Kubernetes stack, we've been able to introduce several innovations that enable to do things in Postgres in a significantly different way. So let me go with these innovations. You may say, we want Postgres to be boring. There's this great tweet by Kelsey Hightower, very well known in the community, that says Postgres is what happens when tech gets so good for so long that it becomes boring, right? And databases are technology that we want it to be very stable. We don't want to risk anything. That's why we call them boring, right? Because we just want them to work. Now, how does Postgres being a boring, which is a good thing, right? Technology couples with innovation. Well, I claim here that being boring and innovating are not at odds. They're not the opposite of each other. And the main idea here is that for sure there's place for innovation in Postgres, but in particular, the kind of innovation we're talking here is not on the Postgres core itself. Postgres core itself is untouched, but rather innovation on top of it, around it, on the stack of components that I mentioned around Postgres, and basically being able to separate, take out some parts of Postgres that may be better handled by other specialized components, as you shall see, and then leverage those to make Postgres expose as a reduced footprint, first place, and then to be able to operate with this whole ecosystem. But the core is the old Postgres that we all know, that is boring and works so well. So where are these innovation opportunities? So there's three areas which, if you really look through the history of Postgres, this 20 or 30 years history, depending on where you want to start counting, they haven't changed much. How do you deploy Postgres? Pretty much the same as, I don't know, 2 decades ago. Well, there's Ansible, Chef, Terraform somehow applies here. Other than managed services, the way you deploy Postgres right now is still pretty much the same as you were doing it, again, long time ago. The same goes with automation.
То же самое можно сказать про автоматизацию. Есть скриптинг, специальные инструменты, которые позволяют оптимизировать. Они тоже играют свою роль. Но помимо этого, можно использовать и эквиваленты для того, чтобы выполнять те же самые задачи.
Is there any way where we can just say some parts of Postgres functionally, we may just delegate them to some specialized component that already exists that may do some of these tasks even better than Postgres? They're not core to the Postgres experience. Sounds mystical, but I'll explain you with examples, real work of this. So how do we do this on the Kubernetes environment? Well, deployment and automation, both parts, can be done by leveraging the Kubernetes APIs and the operators pattern. Deployment is trivially explained by this, especially in the presence of an operator. An operator will expose a high-level interface, typically a CRD or several CRDs. We're going to see on the demo session a lot of this. And you'll be able to deploy a complex Postgres stack with just a few lines of YAML code or JSON, whatever. And in this way, deployment, the way Postgres is deployed, has significantly improved experience by the use of Kubernetes operators. The same goes with automation. Instead of creating shell scripts which are prone to failure and goes as far as they go in automating some parts that are more complicated, especially in the context of how do you automate tasks across different servers. So in other words, on a distributed environment, there's something that somehow can be handled by Kubernetes APIs. Also, with the help of the operators, we can coordinate tasks and dependencies across nodes on a distributed cluster with significant ease of use. It's not trivial, but it's definitely doable. Whereas with shell scripts or other automation tasks, it's quite hard to do. And finally, how do we innovate in terms of offloading functionality? Well, by looking into the Kubernetes ecosystem. The Kubernetes ecosystem has exploded and is exploding right now. And there's a lot of very specialized tools that we can use to leverage and to try to offload some parts of the Postgres functionality. So let's look into the core of this talk today, which is how to deconstruct Postgres, how to take this monolith that we know that is Postgres and see if we can shake it a little bit and maybe rip off some small pieces that we can offload to some functionality external to Postgres itself. So what is the agenda? Which topics are we going to cover here? I'll just go directly with them. There's 6 key areas that I'm going to be talking here today. Let's look at the first one, Envoy, which, by the way, there's going to be another talk tomorrow, starting at the same time as this one on this conference about this topic. So if you're going to dive deeper into this topic, I invite you to come to my talk with Fabrizio, my colleague Fabrizio. We'll be talking about this in more detail. That I mentioned that one of the problems that we face on a Postgres stack is the entry point. And we can solve this problem by using a proxy. We were looking at this problem in detail, and we found that one of the proxies most used in the Kubernetes and cloud native ecosystem, but obviously not restricted to it, is Envoy. Envoy is a great proxy developed from scratch several years ago, very high performance, very wide ecosystem, very well tested and running in so many production environments. And Envoy is quite interesting because it has a plugin architecture similarly to Postgres extensions, by the way, or to plugins in browser that allows you to support different protocols and different capabilities of Envoy. So we pulled together in Congress and some other teams with the Envoy community to develop a specialized filter. They're called filters for Envoy that will understand the Postgres protocol. So Envoy can proxy TCP traffic. Most people know it because it proxies HTTP traffic and does miracles with it. But it also proxies TCP. So Envoy as is can work perfectly to just proxy Postgres traffic, but it does nothing with it. Thanks to this filter that we implemented in Envoy, it is obviously all open source, then Envoy is able to decode the Postgres protocol. By doing so, Envoy is able to extract metrics from the Postgres wire protocol, and because Envoy is already capable of sending these metrics to collectors, metrics collectors such as Prometheus, then we can push metrics to Prometheus of the Postgres protocol. What does it mean? This means that, for example, just by fronting Envoy with the Postgres filter in front of a Postgres database, the traffic will flow through it and it will capture metrics on the fly. So we can expose to Prometheus metrics like such as inserts per second, updates per second, deletes per second, connections per second, transactions per second, rollbacks per second, errors per second. There's like 30, 40 metrics already exposed right now that you can have them graph nicely on a Grafana dashboard if that's connected to Prometheus. And these all, if you think about it, comes absolutely for free. Postgres is not even aware of this. You don't need to install any extension into Postgres, which may cause Postgres to be restarted. You don't need to configure anything. You don't need to do queries to Postgres just to gather these metrics. Just by proxying Postgres with Envoy with this filter, Postgres filter, it will capture all these metrics, send them to Prometheus, and then proxy the traffic to Postgres, which will not be aware of this metrics collection whatsoever. So this is quite interesting because it already increases Postgres observability basically for free, with no interaction, no harm on Postgres in terms of performance or extensions or restarts or anything. But we've gone even further. And for Envoy 1.18, which should be out by March 31st at the end of this month or early April, there's going to be, it's already committed, support for offloading SSL. This is a major milestone for this Envoy proxy filter because it will allow to turn off SSL in Postgres. By having Envoy with this filter fronting Postgres, you'll be able to decode SSL at the Envoy layer. And then if you're connected via Unix domain sockets or in Kubernetes land as a sidecar to the main container, again, also by connecting by Unix domain sockets, but operating on the same sealed space, then you can connect from Envoy to Postgres without SSL. This means that not only if you're relieving Postgres from all the effort of doing SSL, computational effort, but also you're relieving Postgres from doing all the certificate management. Enabling SSL or rotating a SSL certificate in Postgres means restarting the database. And restarting the database may not matter much on your laptop, but on a production environment, it means downtime. By the time the database restarts, you need to stop the connections, and there's an effective downtime, maybe seconds, maybe a few minutes, but it's downtime. This might be a significant problem for many production environments. But by offloading SSL to Envoy, Envoy has the capability to change in all configuration, including SSL, dynamically via a set of APIs. So not only we're relieving Postgres from the effort of having to decode SSL and manage SSL, but we're also relieving it from the role of having to manage certificates. So this is, for me, one of the best examples of how we can deconstruct Postgres and offload functionality to components of the cloud-native ecosystem. We just take Envoy proxy, which is a very, very good proxy, very high performance. We develop a specific filter for it for understanding Postgres, and then we decouple SSL from Postgres and let Envoy do it. If you're interested, there is a presentation on, there's a blog post that we have had as a guest blog post on the CNCF, the Cloud Native Computing Foundation, talking about this blog post. I recommend you to check it out. And there's even more functionality that is going to come into the future. So stay tuned, because there is a lot of functionality coming to this Envoy filter that that will enhance the Postgres experience. And as I said before, if you want to know more, join us on our talk, Fabrizio and I's talk tomorrow, starting at the same time as this talk. Now, how it works from an architectural perspective, just to make this a little bit more tangible. Normally, let's say that we're operating Kubernetes, so we have Postgres as a container running inside of a pod, and we have a user that connects to Postgres via the Postgres wire protocol, right? Pretty simple stuff. Now, if we would just use the TCP filter that came with Envoy since a long time ago, in other words, that is able to proxy TCP traffic, this Envoy proxy can be another container running as part of the same pod that is called Kubernetes sidecar, right? And so we have a sidecar Envoy proxy next to Postgres container, and the traffic now is intercepted by the Envoy proxy and goes to the TCP filter. And then it speaks a wire protocol. It's just basically it's a pass through. This lets the Postgres the protocol, the wire protocol, go through it, and exports a few metrics to Prometheus, but are basically bytes per second in, bytes per second out, connections in, connections out, which is already helpful. Could actually let us troubleshoot some, for example, queries returning a lot of data. Sometimes that's useful. But let's look at this picture, how it looks like when we add this Postgres filter that we developed. By having this Postgres filter, as I mentioned before, understands and decodes the Postgres wire protocol and is able to export to Prometheus additional metrics. But these metrics are now very rich. Are what I mentioned before about inserts, updates, deletes, connections, transactions, errors, and a few other commands that are all decoded as counters. In other words, they can be graphed or varying over time. They're all exported to Prometheus. So we have a lot of rich metrics. And when we add this SSL functionality, there's yet another filter, which is based on the start TLS extension that takes as input the key and the certificate, and then is able to decode the SSL protocol. So the user is connecting via SSL, but this SSL stops at the Envoy layer. And to Postgres, it only goes normal unencrypted, basically, Postgres wire protocol. So we're able, just by using Envoy with these filters, to not only enhance Postgres observability significantly, but also to offload SSL functionality and certificate management without Postgres even knowing about it. So this is why I mentioned this is a great example of how to decouple this functionality to deconstruct Postgres and to rip off a small part of it, which is in this case is SSL management and monitoring, part of monitoring. It doesn't cover all the monitoring that you require for Postgres. It's definitely part of it, enhances the observability and offloads to a separate component. Just as a graphical representation, this is what it looks like on Postgres. We use Envoy in Postgres, and there's a web interface. This contains the specialized dashboards, and this is showing metrics, for example, in this case, from exported by Envoy, like including logins per second or sessions encrypted or non-encrypted. Let's talk about logs now, that I also mentioned before. That was a key component of Postgres stack, that we cannot go to every container, every server, SSH, CD, grep, whatever, just to try to understand what happened. Logs, in our opinion, should be going to a distributed component outside of the database with its own storage, collect it all together so that whatever operation I want to do with these logs, grep, query them, run a PG badger, whatever it is the case, that they're all together in the same place from all the instances or all the pods in Kubernetes terminology coming to a single central location, right? Especially also to avoid problems with partitions filling up or log writing overwhelming the database. That can also happen. So what if we just think about a system which has few dependencies? Because as I mentioned before, one option is to run on ELK stack, but that's a very heavyweight, let's say, stack with a lot of components and dependencies. Can we just devise a system where we'll send all these logs to a central system where it has not only less dependencies, but that is well known to us? We're Postgres people, right? We love SQL. right? I hope so. I definitely do. So why don't we send Postgres logs to a database? Okay, which database to pick? Should be obvious, right? Postgres. So why don't we send the logs to a separate Postgres database? Well, you may say separate database, may not be performant enough. But I'll show you later how we use timescale extension for time series data and inject the logs into a database that is Postgres with timescale, which supports high velocity and high volume of logs. So how will this look like from an architectural perspective, which is what I'm interested in showing you today. Let's look at a pod. Again, we're Kubernetes land, and there's a container which is running Postgres. And let's say we configure Postgres to produce CSV logs, which is one of the configuration options for Postgres. Now, the logs are produced inside a container by default. And container storage is ephemeral, which means, if the container dies, the logs are lost, and it may also fill up at some point, right, depending on the system. So what we do with these logs? What we can do is connect a sidecar, again, another container that runs within the same pod that is based on FluentBit. FluentBit is another cloud-native CNCF ecosystem tool that is specialized on this task, on log collection. Again, look at the pattern I'm trying to bring today. By leveraging tools that already exist on the cloud-native ecosystem, we're going to try to offload functionality off of Postgres or improve, enhance the functionality that already exists in terms of monitoring or log capture or equivalent. So FluentBit is a very lightweight agent. It's written in C, and it's able to collect the logs, apply some log enrichment. It adds, for example, information about the pod and the system where it's running, Kubernetes environment, and then it's able to send them somewhere else. So in this case, the ephemeral storage within the container is just used as a buffer for before the logs are collected by FluentBit and pushed them out. As soon as these logs are pushed out of FluentBit and received like a collector, as we're going to see right now, they can be removed from the ephemeral storage as part of the Postgres container, and they can be rotated. So basically, we're just buffering and then sending to FluentBit, which is collecting the logs, running inside of a container, which is a sidecar to Postgres, and then they're going out. Where they're going, there's another component coming from the cloud-native ecosystem called FluentD, which is a logs collector, basically. It is a tool specialized on receiving flows of logs from potentially many locations. So in other words, it can be multi-tenant and supports collecting the logs from many distinct locations, many distinct components, and is able to collect them. And where does FluentD stores these logs? It's not defined. FluentD does not store logs, it just collect them and then forwards them somewhere else. In this case, this else is what I mentioned before, a Postgres database with a timescale extension for time series data. And so we use a plugin for FluentD, which is able to store the logs into Postgres. There's some transformation behind the scenes because the inner details are basically that the Postgres logs may contain, even though in CSV format, they contain multi-line records, and multi-line records are not handled perfectly by FluentD. So we use some transformations before inserting them into Postgres to just avoid a FluentD management problem with line breaks. But in a sense, the logs flow from the Postgres ephemeral container to FluentBit. FluentBit forwards to a central multi-tenant, potentially multi-tenant FluentD instance, which stores them on Postgres and timescale. So now, how do we query these logs? Because they're coming from all pods on the system, right? All servers. They're coming to this central location. Well, one option, this is a Postgres database. So just connect to the Postgres database and do SQL commands, which was what we wanted at the beginning, right? Just be able to query with SQL these logs. The second option is that we have developed a third component, which is a controller. And this is basically a REST API, which exposes an interface to query the logs. So now you can query these logs via SQL by connecting directly to the database. You can query the logs by using issuing commands to this REST API via normal API clients, or because Postgres, as we shall see later, comes with a web interface. The web interface has an option to show these logs and calls this API. So you can basically see the logs on a web console. This is more or less how it looks like to check the logs on the web console for your information, but we'll see them on a live demo later on. In summary, the features that comes with this functionality are that we are collecting currently the Postgres and Patroni logs. Patroni is a software for high availability, also used in Postgres. And this is work in progress. We are adding more logs functionality. Next item, we're going to also try to collect PG Bouncer, because Postgres also uses connection pooling via PG Bouncer, and to also collect PG Bouncer logs and send them through the same interface to be able to query them all together. This architecture basically creates what we call a distributed log server, and this distributed log server is multi-tenant. Not only it supports collecting the logs from all the pods of the same cluster, but also supports multi-cluster. So if you want to collect the logs from multiple clusters, all the pods of multiple clusters, you can do with a single instance, or you can create multiple instances. That's your choice, right? So, but they're multi-tenant by default. And as I mentioned before, you can query them with SQL or via the web console. Some questions sometimes arise about the use of timescale. First of all, we use the open source version, the Apache 2 licensed version. And we also use timescale for log retention management. So Postgres, when it collects its logs, also will retain the logs for the amount of time that you can specify on an optional retention policy. And then because it uses timescale, it uses partitioning and basically deleting all logs that are no longer held by the retention policy is as trivial as dropping partitions. So it's quite convenient. This is all automated for you. You don't need to worry except specifying what retention policy do you want, and it will be managed automatically by you. This is another example of innovation in Postgres. As you can see, it doesn't affect Postgres core itself, the Postgres operation, how you connect with Postgres or run queries. It just separates another component, which is usually quite important for production usages, for troubleshooting especially, but at the same time, an area which before there hasn't been much innovation before. And we have created this system to send the logs to a distributed log server, which is a Postgres database, which does handle automatically rotation and which exposes both a web interface and a SQL interface for you to query the logs. Let's look also a little bit about architecture in general of how we structure components on Kubernetes. So you basically know that in Kubernetes, the basic unit of deployment is a pod. A pod is just a term that implies kind of an abstraction, the kind of abstractions that containers offer as a dedicated potentially storage space, process space, and IP networking space. And a pod may contain one or more containers. This normally there's like a main container. In our case, is Postgres, and there can be other containers which hold additional functionality. These are called typically sidecars because they implement this side functionality, right? Now, if you think about what is a container is just a process hierarchy, which this means is that there is a hierarchy of components that processes, that start on a root process, and this process may fork and have children, right? But it's a single rooted hierarchy. If you look at a VM, there might be multiple processes, multiple roots. There's an init system, which is the parent root, right? But hanging from this init system, there might be multiple processes. But a container, in reality, is just a wrapper of a process and its children. So it's not a good practice to have multiple processes running inside a container unless they are typically inherited from a single parent. So containers should be basically initless from the perspective that should not have an init system to spawn multiple processes. They should have specialized processes running from a single hierarchy, and then instead of bundling everything together into a single huge fat container, split it into separate functionality and have these separate components as sidecars. So knowing it, how did we structure this in Postgres? So basically, here you see the whole pod. And inside the whole pod, there's going to be the main container, which in this case contains both Patroni and Postgres. And someone may say already, oh, but you're having two things there in the same container. That's breaking your principles. In reality, it's not, because Patroni is actually a parent process for Postgres. The way Patroni works is by basically starting and managing the Postgres binary. So it creates a single hierarchy. There's no init system to run both Postgres and Patroni. Patroni is the parent of Postgres. So it's still a single process hierarchy what we have on this container. And this container connects, has a handle of a persistent volume of a PV. It's called a PVC, persistent volume claim. All right, so this is the main container. Now, as I mentioned, in Postgres, we have connection pooling that sits in front of the database. This is an optional component. You may turn it off if you want to. We'll see later. But it is very good to separate a separate container, because within a pod, they can connect via Unix domain sockets, as you can see on this picture. But at the same time, we are, by using this connection pooler here, we're able to limit the number of incoming connections going to Postgres, or we can set the max connections as a lower value, which in turn makes Postgres operate on a more efficient regime. It's more optimized configuration and so forth. I'm not entering into that discussion, but basically we can have PG Bouncer as a separate container, as a sidecar to Postgres, and within the pod they can connect via Unix domain sockets. Now, we also have Envoy, as I mentioned before, that we use for SSL uploading, for enhanced monitoring, and for future uses in the future. So Envoy is going to be yet another sidecar. Envoy connects to via PG Bouncer for handling the connections, also via Unix domain sockets, as well as directly to Postgres for the replication traffic. This is because PG Bouncer doesn't handle replication traffic. So when we have Envoy and PG Bouncer, the normal data plane, the normal connection goes through Envoy and then through PG Bouncer before going to Postgres, whereas replication traffic goes directly from Envoy to Postgres. In both cases, all connections happen via Unix domain sockets for maximum performance. And this is a very, I would say, well-architected way of connecting to Postgres, which exposes the SSL offloading, the enhanced observability, and connection pooling, and all this transparent to Postgres. Just connect from the outside of the pod to the port, and then it's packed to you. It's transparent. You don't even need to know that all those components are there, but they offer all these benefits. And as you can see, Envoy is yet another sidecar. This sidecar on one side exposes these metrics to Prometheus, and on the other side, it exposes a couple of ports, one for Postgres connections, one for replication connections. But if we're looking at the anatomy of the pod that we have in Postgres, there's some more sidecars in this case, right? One of them is Postgres util. Postgres util, if you really think about it, what I was saying before, a container is just a hierarchy of the processes and the process of its and its children that perform a task. In the case of Postgres, Postgres spawns many other processes, but they all start from the same root. But what about administration tools like pSQL, right? Where are those tools located? Within the same container as Postgres? Well, definitely that's something we can do, but in my opinion, not necessarily. The goal of containers is to basically pack the minimum number of assets that are required to run that process. pSQL is not required to run Postgres. I may not even need pSQL ever within the container. So this is a separate container that right now is started by default. In the future, it's going to be set up as an ephemeral container, which means a container that you will only create on demand whenever you need it. But for the time being, it has to be, for compatibility reasons, always turned on. But because we want to enforce very strictly this separation of concerns, tools for administering Postgres go to a separate container. Anyway, the separate container may connect via Unix domain sockets to the main Postgres Patroni instance. So there's no performance degradation by doing this. Now, we also want to export metrics to Prometheus that are not exported by the Envoy filter, because some metrics really need to query Postgres. So at least as of today, we'll look into the future because we also have some ideas here. But for now, if you want to query the Postgres catalog, you still need to query Postgres, right? And that gives you a very rich metrics that that in our case we want to expose to and export to Prometheus. So we have another sidecar container running here, which is the exporter that runs a well-known Postgres exporter component that connects to Postgres. We also connect to PG Bouncer to also expose metrics from PG Bouncer, and from all the databases that we have in the Postgres database, they're all exported to Prometheus via this exporter. But remember, there's distributed logs, and I also mentioned this FluentBit component that I already mentioned that was a sidecar running within the same pod. So here we have also FluentBit sending the logs to FluentD. And also, whenever we take a backup, and Postgres handles backups automatically for you, there's agents. And agents are jobs that are created within the pod because they also need to connect directly to the Postgres container to run the commands to basically take the backups, right? To run PG-based backup and access the file system. So this is at the end of the day, the anatomy of the pod may look a little bit complex, but in reality, all this is transparent for you. There's nothing that you need to do. This is all done automatically, and it just enforces this principle of separation of concerns. Different tasks are handled by different containers which have their own minimal footprint, and they're prepared to work together. In the future, it's not implemented right now. There's going to be yet another component called the local pod controller. This is going to be a small container that may end up basically even substituting the functionality of some other sidecars here, which is kind of a operator. You know, in the operator pattern in Kubernetes, there's CRDs and there's controllers, and we're going to have a local controller for the pod, which is basically a software that is going to be handling reconciliation loop connection with Kubernetes, but needs to perform local operations on the cluster. There's some binaries that we need to call to perform central operations that inside of the pod, and it's better to have some controller that is local to the environment, whereas having to running execute commands on the pod. So this is an optimization for the future. Will also bring significant benefits, but it's not present right now. But when this is going to be the case, there's going to be this local pod controller here. All right, this is the architecture of the pod, right? Like what we have here is the whole view of the pod. And now, what does it look like the whole architecture of a cluster? So let's zoom out a little bit right now, and we'll see that we may have several pods across the cluster. One is going to be the primary. The other ones are going to be replicas. They all have their own independent storage. Now, in Postgres, to solve the entry point problem, apart from having the Envoy proxy, we expose services, Kubernetes services, which typically are associated with a DNS entry. And there's two services that are exposed by default. One called name of the cluster -primary, which exposes a read-write connection that always points stable to the master. And one called replicas, that is a load balance service that connects to all the other replicas. You can see in the diagram here. Then there is the Postgres operated services. We may have the distributed log server to collect the logs, as I mentioned before, which contains the API, which is the distributed log server itself, with a FluentD component and the Postgres plus timescale database. This is used to collect the logs remotely. Then there is the Postgres controller itself, the Postgres software itself, which contains two components on itself. The controller, which speaks, is basically listening on the Kubernetes API, reacting to changes, and is basically running what it's called the reconciliation loop, reconciliation cycle. And a REST API. This REST API does two things. One exposes an API, so you can also manage everything in Postgres with an API if you want, but also is able to power a web UI, a web console that Postgres comes with, that I'll show you later during the demo. So this is more or less the whole picture of what all the components look in the Postgres architecture. Now, let's go a little bit faster here. This is more or less well-known, the integration with Prometheus and Grafana. We have also done this in order to try to streamline and also externalize monitoring from Postgres to more cloud-native components. Now, integrating Prometheus and Grafana is pretty much easy, right? It's trivial. So what we have done beyond this? So we have the Postgres exporter, but we have also implemented a PG bouncer exporter, which actually uses a quite neat trick by using the Postgres extension DibbleLink to connect remotely to the via PG bouncer. So to connect to Postgres and Postgres to PG bouncer to gather the metrics, and to connect to all the databases present there to gather all the metrics from both Postgres and PG bouncer and all the databases within. But we didn't want to stop there, and so we're providing customized Grafana dashboards, which are heavily optimized for Postgres operations. So it's just not the dashboards that may come from the default. It's dashboards created by our team of experts, Postgres DBAs, which have decided which dashboards do we want to see when we administer specifically a Postgres cluster. And the same with alert managers, alerts. So if you know the Prometheus and Grafana, they also have a component called alert manager, which can trigger alarms when certain thresholds or events happen. And we also provided a lot of customized alert managers. You can customize your own, but if you like the ones that we bundle by default, you just need to connect to your alert technology like PagerDuty or Obsgenie or whatever you use, or Slack, and you'll get paged when any of these alarms are thrown. And last but not least, and I'll show you these, we have integrated these Grafana dashboards into our own web interface. So within the web interface, you can connect to the dashboards. This is how it looks like, but we're going to see as part of the demo. So I'll just move forward. And the last part that I wanted to mention in this presentation session is, sorry, not the last one, but the second last one, is a mechanism that we have also used on this web interface to provide authentication and authorization. And it's basically, instead of reinventing yet another system for authentication or having another set of users and passwords for the web UI, we're going to rely them, as the topic of this talk is all about, offload these to a component that already runs on the CNCF ecosystem. In this case, we're going to rely on Kubernetes authentication and authorization mechanism called RBAC. It's more authorization than authentication, but we can leverage it for both, for the web console. So how it works? Basically, we have a user, and this user, let's say, authenticates on the web console. We're going to see how the web console works later. It says user HT, password, whatever, and this goes to the web console. The web console is going to submit an authenticate request to our REST API, which is the Cypress operator itself. This REST API is going to look for a secret that should exist on Kubernetes that looks more or less like here, right? It's a secret. This is a standard Kubernetes secret, and this secret has to have a key called password and Cypress username and potentially Kubernetes username, which might be different. When query this secret, the password will be validated, and if it's validated, then the REST API is going to generate a JWT, a JOT token, which will include the Kubernetes username, and this will be returned to the web console. So basically, we're using here JWT authentication, JWT tokens, but the passwords, they're going to be validated against secrets, which are standard Kubernetes objects. Now, we're not leveraging Kubernetes RBAC yet, but stay tuned. Let's now fire a command from the web console. So now let's say we want to perform any operation. This operation, we call again our REST API from the web console, and this is going to include the JWT token. The JWT token is going to be decoded by the REST API, and it's going to extract this field called a Kubernetes username. Now, this Kubernetes username is going to be used to call the Kubernetes API using a field called impersonate. This is a header. You pass it. It says impersonate user this username. In other words, the REST API, which has by default more broad permissions to call Kubernetes API, is going to say basically sue to this user by calling the API. And Kubernetes is going to perform that action, based on the real authorization capabilities of that user. So if that user is allowed to perform that operation, that will succeed. Otherwise, it will not. and then the operation will be performed. So this is how we're leveraging Kubernetes RBAC without having to invent our own users and passwords and authorization mechanisms. We're just using this impersonation header extracted from the JWT token that we generate to call Kubernetes API on behalf of a given user, which typically will have reduced privileges compared to just running, operations with broad privileges. And the last innovation I wanted to discuss here today is what we call the cloud nativization of Postgres DBA operations. So one opportunity that Kubernetes brings us is the automation of what is typically called day two operations. Day two operations are these operations that you need to perform once something's already deployed, installed, running, and you want to start doing maintenance tasks. For example, in Postgres, running vacuums or PG repacks for removing bloat from indexes and tables are great examples of day two operations, right? And Kubernetes brings us the opportunity to automate these operations. The way we have chosen to automate these operations is by leveraging what in Kubernetes are called the CRDs, custom resource definitions, which are very high-level objects that you create on Kubernetes representing a concept. And we have decided to make these concepts very high level, so to expose a top-level interfaces so that all the complexity is hidden behind them, and expose a very simple interface to users. These users, they don't need to be Postgres experts at all, just to understand why you want to run this operation, but not how to run this operation. And just by typing this YAML or JSON files that represent the CRDs, Kubernetes and the Postgres controller will perform this operation for you. So let's look at an example. We call this CRD SGDBOps, which means Postgres database operations. And it supports several operations. One of them, for example, could be make a manual backup. Backups can be automated in Postgres. We'll see later during the demo. But you can also have manual backups. And to create a manual backup, just need to create a YAML file like the one you're seeing on the screen. This is fully functional. This is complete. You may add some extra parameters, but this will work. So it's very simple. You can see in basically the green color the fields that you need to type in, the name of the backup, the cluster you're referring to, and the operation, which is backup, because we also support other operations within the CRD. The way this will work is that you'll basically run kubectl create or apply. This will call to the Kubernetes API. The Kubernetes API is going to persist this information on etcd because this is a CRD. Once this is persisted, this is going to call our operator, the Postgres operator, which is listening on events happening on this CRD. So it's going to call the Postgres operator. Postgres operator is going to realize, oh, someone is asking me to perform an operation on behalf of the user, which is a backup operation. So let's take a backup. And this will all happen behind the scenes without you having to do anything else. It will create a backup job, which will run inside of the pod. And in this case, we use WALG for backups. We'll run the WALG generate command. And then we'll capture, well, obviously the backup will go to cloud storage. And then we'll capture the output of this backup. This backup status is going to go back to Kubernetes API. And Kubernetes is going to, because of our instructions, is going to fill this information as the status part of the CRD. So you see now there's in yellow here in this YAML file has been completed with status part that says the operation is completed with one retry, because you can also program the operation to do several retries if it fails, and is completed. So basically, we have created here a very simple textual interface for users to run behind the scenes what could be potentially complex operations fully automated by just specifying a very simple minimal specification, the part in green, and the result of the operation, the status in general, the messages back will flow you as part of the same CRD in the status field. With this, we have right now implemented manual backups, Postgres benchmarks, repacking the database, vacuum operations, minor version upgrades, major version upgrades, and a few others that are coming down the road. And all these operations are absolutely fully automated. You need to create this YAML file or JSON if you prefer that as a format, do kubectl apply, and watch and sit and relax and see how it works. That's all that you need to do. So this is what I wanted to bring today to this session as part of the presentation. If you liked what I've been talking about for now, feel free to join our Slack and/or Discord communities. This Postgres software, open source, is Postgres.io. Their respective communities are slack.postgres.io, discord.postgres.io. Feel free to join us and ask any questions. What we're going to do now, we're going to have a Q&A session. Then we're going to have a small break to probably there were too many concepts here. So we'll take a 10 minutes break. And after that, we're going to do a full hands-on lab session. For this hands-on lab session, as I mentioned before, I'm going to run it. But feel free to have on your computer your own or access to a Kubernetes cluster. You may run the same commands I'm going to be running with you. At the same time, you'll be able to reproduce this on your own environment. Before jumping into the Q&A session, what I'm going to do is I'm going to create everything from scratch. So you can definitely reproduce this totally from scratch from your home or office or wherever you are. And so I'm going to go now and just fire a command to create a Kubernetes cluster that we're going to use for the demo later. So you also see I really start from scratch. There's nothing prepared. And obviously, this is going to be a demo, and demos sometimes fail. I hope this will not be the case. But if everything goes well, it should run. And I'm going to create everything from scratch. You can also do the same. In this case, I'm going to create a Kubernetes cluster on Amazon. So I'm going to use Amazon EKS for this. If you want to do the same, just have handy your Amazon credentials, and you'll be able to follow my commands. Other than that, you can use any Kubernetes cluster in principle to do this. So feel free to do that. So let me briefly turn off this presentation and look at the steps we're going to take. If you want to follow this tutorial, again, at home, at your office, just go to postgres.io/doc, or let me actually just go directly. The main website is postgres.io. Then go to documentation. It's very simple. And then tutorial. And this is the steps we're going to follow along the way. So for now, what I'm going to do is just create a, I hope the font size is okay. I'll make it big enough. What I'm going to do right now is just create a Kubernetes cluster. Creating a Kubernetes cluster on AKS takes around 20 minutes. So I'm just going to create it right now from scratch, again, because I want to demonstrate you that there's no tricks, no hidden, nothing here. And I'll take questions, and then we'll do the break, and then we'll do the demo. So to create this Kubernetes cluster on EKS, just going to need to run these commands. I'm just going to copy this, and I'm just going to paste here. And I just need to actually set up a profile here. So yeah, I'm going to use an AWS profile. I'm going to create a cluster in the East2 region. I'm going to call it Postgres. It's going to have 3 nodes, 100 gigabytes per node on 3 regions, version 1.17. Let's fire this command. As I said, this will take around 20 minutes. And I am doing this because I want to demonstrate that I'm creating everything from scratch, that there's no tricks hidden here, anything prepared, that everything may fail, but that will be fun. Hope it will not, but in other words, it will be fun. And I'm ready to take some questions, if there's any, which I hope there will be some questions.
Okay, thank you, Alvaro, for your presentation. It was really a lot of information, and I think we will need some time to just understand it. And there is already a question in the chat, and it's a question about backup copy of Postgres, whether it's full or increment.
Yeah, so the backups are using continuous archiving. So from that perspective, it's what's called physical backup. So it takes a base backup from which you'll see later, because we'll do this on the demo. But you can select the frequency and the periodicity where you want these base backups to be taken. And then in between the base backups, all the wall archives are stored. So from this perspective, it's differential backup, because we're storing the wall archives, and you basically incurring almost zero data loss, or zero data loss if you want to restore from them, because as soon as the WAL file is generated, it's also being pushed to the cloud storage. We use object storage for storing the backups. And you can also, if you want to do a PITR, point in time recovery, you can go back to any instant of time as long as you have at least a base backup older than that instant of time where you want to recover.
So you decided to go with base backup and not use any other tool for backups. It's like enough for your system.
No, actually we use internally WAL-G, and we use WAL-G to generate the base backups on the given schedule that we specify them to run, to push the WAL files as soon as they're generated, the WAL segments to be more precise, and to also manage the lifecycle of the backup. So basically, we'll see later, but I can quickly go there if you want to see. But if we go to the backup configuration, we'll see that you specify as part of the backup configuration, we'll do that demo here later, but a cron schedule, which is when you take the base backups, how many of them do you want to retain, and everything else will be fully automated. There's nothing you can do. According to this configuration, which is only for this tutorial, but obviously, a backup will be taking every 5 minutes, base backup, and 6 of them will be kept. So basically, you'll be able to keep 30 minutes of backups. Obviously, this is only for demo purposes. But other than that, you'll have basically 6 base backups always taken, or less. And whenever a new one is created, the other one will be deleted automatically. And then in the meantime, all WAL files are being backed up automatically.
Great, thank you for this answer. And also there was a question, maybe even a little discussion in the chat. Which persistent volume do you recommend to use under Kubernetes with Postgres?
Well, that's a broad topic. It really depends on the environment in which you are running. We are quite agnostic because we want you to run Postgres on any environment that you want to run it. But obviously, typically, you're going to be running so we need to distinguish on-prem and cloud environments. So if you're going to run on a cloud environment, I typically recommend that you use network disks. If you're on Amazon, it will be EBS. If you're on Google, it's going to be persistent disks and so forth, because they're highly reliable. They may not be the best performance at times, but they're highly reliable. And Postgres just basically asks you to provide a storage class. So any way you want, you can do it. You can create a storage class and just specify that storage class when running the cluster. We'll see how to do this later, and it will just use that storage class. On-prem is a different story. And on-prem, but also applicable to cloud environments, you can use technologies like OpenEBS, for example, to create your own distributed volumes, which again will be exposed as a storage class. It's very broad topic. There's many options, but we are quite agnostic. The only thing that we require is storage class. However you create that is really up to you.
Okay, thank you. And next question, are you planning to use 8 containers in one pod?
Yes. At some point, we will also reduce that number. As soon as we introduce the local pod controller, that local pod controller is going to eventually grow in functionality and start absorbing functionality of some of the other containers. For example, the Prometheus exporter, it's going to be absorbed eventually by the local pod controller. And so at some point we'll have 8, then we'll have 7. And we also want to coalesce some other functionality into other containers into the future. Like, for example, we'll try to also implement connection pooling in Envoy proxy. So we may be able to remove the connection pooler.
Cool, thank you. And speaking of Envoy, I would love to ask, are there any security issues with such proxy?
I'm not aware of. From an architectural perspective, there should be no difference by using Envoy as a security proxy, as a proxy, than not using it. There will be if, for example, you would use Envoy to offload SSL and then have an encrypted connection from Envoy to Postgres that goes across a wire. In this case, yes, you're just transmitting data unencrypted over the wire. In the case of Postgres, Envoy is a sidecar to Postgres, so they run within the same pod, so that connection cannot be tapped. And that's why we use Unix domain sockets and unencrypted connections. If you run it a different way, that might be one of the potential problems that I can think of. There's also, right now, there is no HBA, host-based authentication in Envoy, which, by the way, is being discussed these days. So we also want to offload HBA authentication to Envoy and actually be able to stop, for example, kind of denial of service attacks at Envoy before reaching Postgres. But right now, Envoy will just let pass every connection. It will have to be, as of today, again, Postgres that stops connections that are not authorized to connect to the database.
Thank you. And next question, how do you guarantee that OM killer not occurs on Postgres container?
Sorry, I didn't understand. What may occur?
OM killer.
Oh, yeah. Well, that's a hard one, right? This may occur with or without pods. So the quick answer is that if it happens, the nature of Kubernetes and the Postgres operator will just trigger, first of all, that the container will die. This means that some other replicas will be elected as a primary node. The services will be readjusted, and there will be small downtime on the database, but you'll have a new primary node, and this node will recover eventually. This will all happen automatically and transparently for you, but obviously it's not ideal. So there's many reasons why an OM may occur on Postgres. We are taking some measures like configuring SAHM size appropriately on containers, which is not appropriate by default for Postgres, which uses a lot of shared memory, and a few others. But in reality, it really depends on how you configure Postgres. If you configure Postgres to use more memory than available, OM will kick, right? But that's not different from what may happen on a physical node. We have some, actually, Postgres, you may go to our issues. They're all open. They're on GitLab. We have an open issue to consider using Facebook OMD, user space OM killer, to ease these problems before they may happen. It's not very developed yet. But again, as of now, the situation is slightly better, I would say, than on physical virtual nodes not handled than on Kubernetes.
Okay, I see. Thank you. And the last question in the chat so far is Postgres a Kubernetes operator?
Yes. We typically say it's more than that because an operator is typically just concerned by deploying something, and what Postgres is a stack of components around Postgres and a lot of automation and a lot of validation. And we just call it a platform for running Postgres on Kubernetes. But if you want to be like very, very strict and correct, it is definitely an operator.
Mm-hmm. I see. So there are some more questions. Do you think we need to stop them at some moment because you want to leave more time for your masterclass, or we can continue?
Yeah, I would say let's do a small 10 minutes pause here to also be able to make a demo. I would love to make a demo, and we can take questions along the way or at the end of the demo, or obviously there's this virtual room after the session where I'll be happy to take further questions.
Mm-hmm. Okay, so thank you so far, and yeah, I think the question in the chat, which is the last one for this Q&A session, is how do you tune Postgres configuration in Postgres containers? Is it automatic tuner or something else?
I'm going to show this as part of the demo, how you to ship your own tuned Postgres configuration. We are providing a very well-tuned configuration by default, which is much more tuned than Postgres default configuration, which is not very well tuned, let's say that way. We're tuning around 30-40 parameters, and you can see how and which ones. But other than that, we're not doing any auto-tuning for now. It's a quite broad topic. There's even a specific company just doing this. but may come in the future. Definitely, there's ways for doing this because there's a lot of automation built into Kubernetes that may allow us to do this. But it's just right now the functionality is that we're providing 30 to 40 approximately already tuned parameters for you for that are general case, and you may on top of that ship your own tuned configuration, which is strongly validated before applying it to the container, and just create a YAML file with the configuration and we'll apply it for you automatically. Stackers will apply it for you automatically.
Great, thank you. And speaking of configuration, I want to thank you personally for PostgreSQL core.nf, which is just great.
Thank you.
So, Alvaro, you're welcome to run your masterclass. I wish you good luck.
Spasibo. Okay, so let's continue. Apologies for the technical issues, but I hope that you'll have had some time to take a longer break and get prepared for the lab session. So first of all, if you haven't done so, please go ahead to this website. So stackres.io, then go to documentation, and then go tutorial, the section number 3. Right? We're everything I'm going to do is on this web page. You can do this with me. You can do it later. If you have a Kubernetes cluster handy where you can fiddle around, feel free to just do this by yourself. The only thing I've done so far, I was running just before the demo, was this command to create manage Kubernetes cluster, so EKS. I just copied and pasted this into my shell. It produced an output similar to this. We can just check, but basically it created the cluster. There's nothing special here. This is not about Stackers at all. This is just about creating a managed Kubernetes cluster, just to check that everything's okay. I'll just show this. I hope that you can read the font okay. Let me know otherwise. Here we have a Kubernetes cluster. We should have 3 nodes. Yeah, and other than this, the Kubernetes cluster is empty because I just created it, right? So this is if you go on this website, you'll see on the tutorial that there's some prerequisites here. Software installed, it's pretty basic. You just need kubectl, Helm 3, and using a Linux shell. I already have installed this. Then I created a Kubernetes cluster using, in this case, Amazon EKS. This is just to check that everything's okay. So we already have the Kubernetes cluster. Let's look at the next prerequisites. The next is to install Prometheus and Grafana. This is technically optional. You may install and run Stackers without installing Prometheus and Grafana, but you will not have monitoring. And because I think it's something cool to have, let's actually do this. To install Prometheus and Grafana, this is dependent on Prometheus and Grafana installation. They're reproduced here to have all in the same place, all complete. But you should refer to the official documentation for further information. But anyway, let's just go and do it. It's very simple and quick. So first of all, we're going to create a namespace within Kubernetes specifically for monitoring purposes. And there we're going to install Prometheus and Grafana from the Helm chart they have that comes everything together. And so just paste this command here. And this will take 1 minute, more or less, and it will install Prometheus and Grafana in this namespace monitoring that we have just created, and we'll have it ready. Again, this is a prerequisite before installing Stackers. This is optional, but if we don't have Prometheus and Grafana, then we will not be able to have monitoring. Everything else will work perfectly well, but I want to try to show the demo with this. Remember, this is a live demo. Anything may fail. Hope nothing will fail, and if something fails, we'll try to fix it. But let's hope it will work well, and we should get some output here. Excellent. While Prometheus install, I'm going to move forward. We're going to try to do everything a little bit faster, so I'm going to just try to move forward. The last step into having all the prerequisites are to have an object storage bucket ready. This is also optional. We don't strictly need it for installing Stackers, but it's going to be used for backups. So as long as we want to have backups taken, then we're going to be using object storage. So we're going to go ahead and also execute these commands such that we can take backups from Postgres. In this case, it's dependent on the environment. I'm going to use here an S3 bucket from Amazon AWS, but you could use anything. Even if you want to have your Kubernetes cluster running on GKE and then have the backups on S3 or whatever, that's absolutely possible. You can also, if you don't want to run them on cloud, you're running on-prem, I would recommend you to go and use MinIO, which is an S3 compatible implementation that runs also very well on Kubernetes. You can just install it in a very simple manner. But for this case, I'm going to be using a S3. In this case, again, this is not about Postgres at all. It's just about creating an S3 bucket and policies. It's a little bit cumbersome. This is AWS specific. I'm just going to go quickly through it. Just let's sure that, yes, Prometheus is installed. Everything looks good. So basically, if I would say right now, monitoring get pods, we should see that there are some pods running here from the installation of Kubernetes. Everything seems to be ready and status running. All looks good. So we have installed already, created a specific namespace for monitoring, including Prometheus and Grafana. Let's create the object storage, the bucket. So this code is going to create, first of all, it's going to create a policy, IAM policy for the backup. Again, this is Amazon specific. I'm not going to go too much into the details. Let me just, sorry about that. Let's select the bucket name. Let's say this is going to be demo backups Postgres.io. Need to remember this because I need to do this well next time I run this command. So I should have a policy document generated here. Looks good. And now let's run these commands to create. This is going to create IAM user, and it's going to attach this policy that I just formatted. So let's just paste this here. Yeah, let's set the profile to the account I'm going to be using here. And if all is good, this is going to create the user. All looks good. And last but not least, I'm going to create some credentials. This credentials is the credentials I'm going to be using to access the bucket I'm going to be creating later. This is going to output some credentials because this is going to be a live session. I'm just going to redirect this to a credential file, not to show it on the screen, sorry about that, but this is going to be creating the credentials. I'll use them later. And finally, let's create the bucket. No, sorry, that didn't copy. I think it's just. All right, so at this point, yeah, demo backups Postgres.io, it's going to be created. So I have fulfilled all the prerequisites. Again, this is all previous steps before installing Postgres. Everything should be straightforward. Try this at home. Everything is documented here in the tutorial. So let's go ahead with the Postgres installation. First of all, we're going to create another namespace just for the Postgres. So we have one namespace for the monitoring. Now we're going to install Postgres. Postgres as the operator on a specific namespace. So let's just create this namespace. This should be easy and fast. And then let's install Postgres. Let me just copy and paste and start running the command. This will take like a couple of minutes, and I'll explain you what I'm doing here. So this is already running. Let me show you. So basically, we're using Helm install. We're going to be installing the upcoming 1.00 version of Postgres, currently on Alpha 1. So it's a bit experimental, but by the way, it works well. And it's just because it comes with many advanced features. And we're installing Postgres on the namespace Postgres. The name of the Helm chart is called Postgres operator. And then I'm setting some parameters. The end is just the URL where the Helm chart is stored on compressed format. About these parameters, this parameter I need to set in order to be able to automate Grafana into the web UI. So Postgres Web Console, I'll have monitoring is enabled. I'll have the dashboards included in the Postgres Web Console. And these three parameters are coming from the Prometheus installation. So if I have a different Prometheus installation, I may need to tweak these values, such as what is the host where the Prometheus is running, or even if I'm running on a different namespace. This is basically the namespace where I installed Prometheus and Grafana, and the user and password. These are the ones that are come from default if I install Grafana from the Prometheus Helm chart that I used before. So in other words, if you have a different installation, you may want to change these parameters. And finally, I'm creating here a load balancer to expose the web UI, the web console, so that Amazon will create a load balancer in their environment and expose via HTTPS the load balancer. If you don't want to create a load balancer, set this to cluster IP. This link will take you to all these parameters of the Helm charts. There's a lot of options to customize installation, but for the tutorial, let's keep it like this. So once everything is installed, we should get a message similar to this. It should happen anytime soon. And once it is installed, we're just gonna check the web UI. And for this, we're just gonna query. For the web UI, there's gonna be a service exposed on Kubernetes land, and we're gonna have a DNS entry there. We're gonna use this DNS entry to connect to the load balancer and be able to access the web console. I'm gonna do most of the demo from the command line, but I'm gonna go back from time to time to the web console to also show you how it would be done from the web console. But what I want to say is that everything that can be done from the command line can be done from the web console. Everything that you can do on the web console, you can also see the results from the command line. So they are both absolutely interchangeable. So I'm just going to be a little bit go back and forth for you to show you both faces. Okay, looks good. Looks like it's installed already. Let's use this command to get the service name, the URL of the service that is exposed. It might be creating as of now. But basically, this is the DNS where the web UI is going to be exposed. So let's try to access this. Yeah, we're using here a self-signed certificate, so this is expected. And if all goes well, I should be presented soon with the login interface here we have the login interface to Stackers. Let's make the font size a little bit bigger. The default username is going to be admin. The password is automatically generated, so we need to query it. There's here a quick command to capture the password from that it was automatically generated. I'm just gonna pipe it to clipboard. Again, we are on a public session, so I'm just gonna copy it to the clipboard, and I'm gonna come here to paste it. It's pretty long, the generated password. And okay, good. So we've got access to the web console. This is Stackers web console. We'll come back here later. The most important thing that I can mention here is that it also supports dark mode. I'm gonna go with dark mode for now. All right, so let's continue with the tutorial. We have installed Stackers. As you can see, installing the Stackers is just one command. You may specify some options to customize the parameters, but installing Stackers is helm install and this command. So it's pretty simple and comes with a lot of powerful stuff, including this web UI that we're gonna be seeing. So let's look at how to create a very simple cluster. And one of the goals in Stackers is that we want to make two things: A, Postgres easy, easy to operate, and especially easy without having prior Postgres knowledge. Because we're all on Kubernetes land and we're using Kubernetes tools, we're also trying to leverage Kubernetes best practices and what Kubernetes users are used to, so that if you're a Kubernetes user, if you have Kubernetes experience, you're going to become a Postgres expert too, without having to know Postgres. So one of the things we're trying here is to make it simple, to try to hide all the complexities about Postgres and connection pooling and high availability and monitoring and backups and many others, which can become quite complex and may require significant expertise in Postgres. We're trying to hide them behind very simple interfaces that any Kubernetes administrator, even not an advanced one, may understand, may be able to operate with. But the second one is that the result of this, even it looks very simple, it is enterprise grade. It is Postgres clusters created with all the components to run directly in production, with all the best practices that our DBA expert DBA team has built into them, and you may deploy this into production. So it's very high quality components with a lot of moving parts behind the scenes, all prepackaged for you and exposed with a very simple interface. We're going to see now the most kind of probably extreme simple example, but you'll see how easy it's to create a Postgres cluster with Postgres, with a lot of components inside of it. As you may know, in Kubernetes, you may use CRDs. I also mentioned this before, but just to recap, a CRD is a custom resource definition. It's a custom object in Kubernetes. You may think of Kubernetes as an object server, and also supports custom objects, like Postgres supports custom data types, right? And we're gonna expose these custom objects with very high-level interface, so you don't need to worry about the internals of Postgres, unless you want to, which you can, of course. And these CRDs are typically created as YAML files. Syntax also allows you to use JSON. I'm going to be using YAML here. It's less verbose. And so let's just create a YAML file and let's apply it on Kubernetes. And this is going to create clusters for us. It's as simple as it sounds. So let's look at this file. We're going to create this simple cluster. Let me first copy and we're going to be creating it here, right? So let's just say cut to this file and copy these contents, right? So this file just basically says we're going to create an SG cluster. This is the name of the CRD. I'm going to call this cluster simple because it's very simple. We'll see that we'll create a more advanced cluster later on. I want to have 2 instances. I want to use the latest available Postgres version. This will resolve to a specific minor version number. And I want the pods definition to, within the definition of the volumes, to contain a 5 GB volume. This is as simple as it can get, right? And this, 10 lines YAML file is going to create a Postgres cluster with 2 instances, with connection pooling, with high availability built in, and with Envoy proxy, with a lot of components. Let's just go and run it. To run this, we just say kubectl apply-f and the file we just created before. And if all goes well, we should see the pods creating very soon. We can check this, for example, with this command that will watch for the creation of pods. And here we have simple 0. The simple 0 is going to be the first pod is starting to be created. We can also go back to the web console where we already see that there's a simple cluster here, and here we see that it's pending state, so it's effectively created. This is what I'll refer to that what you do on the command line interface. I'm just going to make the font size a bit smaller. Yeah, so it's clearer. What we see on the command line interface cooperates with the web UI and vice versa, right? So here we see the cluster creating, and very soon it will start populating the containers, and then we'll go to have a second cluster. Okay, good enough. Yeah, there's already initializing. So while this creates, let's look at what is going to be the next steps. So this is a simple cluster, and it will contain this components. It will include Envoy proxy. It will contain monitoring. It will contain connection pooling and the optimized configuration. Now, let's say that I want to optimize the configuration. I want to use backups. Right? Backups are not going to be enabled for this cluster for now. I want to have the distributed logs that I mentioned to you before. In this case, we're going to go and follow the steps to create a more complete cluster. How it's called here, and we're going to learn some concepts along the way. Just before going that, let's check that this is gonna exist, and we can connect to Postgres to also demonstrate that there is a Postgres database behind the scenes, right? So, okay, looks like cluster number, the first instance is running, and the second one is almost to be ready. So that will be very good news. Yep. Okay. We have our cluster with 2 instances, and each one has 5 containers right now. If I go to the web UI just to check it effectively, here we have the 2 containers. Both are active, and this one is the primary. So let's demonstrate first of all that there is a Postgres here. One thing we can do, this you can also see from the tutorial. I'm just going to do it directly, but you can see from the tutorial that first of all, we can just connect via physical. So if you remember, there's a container called PostgreSQL, which contains Postgres administration utilities, and we can just execute a command inside this container and connect to pSQL. Actually, I'm just going to copy because I prefer to go a little bit faster, have a little bit less time than planned. and just run the command, I should be able to connect to Postgres. This is pretty simple, and here I have Postgres database, right? So good. As you can see, again, with one very simple YAML file, we have created a Postgres cluster with one replica in this case. We can just edit that number of replicas, and it will create a third replica. It's very simple. It's built-in high availability. If I kill one node, the other one will become the primary, and another one will be spin up automatically. We can also demo this. It's very easy. But let's just move on. I also want to show you how to connect, because this is actually at the end of the day just running a command. But how do I connect from, let's say, my application? Postgres exposes, as I mentioned before, 2 services normally per cluster. One for the read-write workload, one for the read-only workload. The read one is called name of the cluster / primary. And so I can also connect externally from this. To connect to this, what I'm going to do is, first place, I'm just going to copy this. I'm just going to launch an application. In this case, the application, I'm just going to run another pod with Postgres, but this Postgres pod contains the command line psql, but this is external to the Postgres cluster. So just think of a web application that is going to connect to Postgres. And if I just exec here, yes, so we'll see that there is psql here, right? This doesn't know where to connect, but there is psql here on this other pod. Now, when I'm going to connect from the outside, I need to connect with the user and with the password. It's going to be password authentication by default. What is the super user password? This Postgres cluster that I was created, I didn't specify any password, right? And that's on purpose. By default, it's automatically generated, and it's stored in a Kubernetes secret. However, I can easily query this from this command. So what I'm going to do is I'm going to run this command. Again, because we're in a public session, I'm just going to copy this to the clipboard. And this is going to be the super user password that got automatically generated when I generated the Postgres cluster. And I'm just going to now execute a command on this external pod, so external to the Postgres cluster. And I'm just going to say connect to the simple primary, which is the name of the service that is exposed, because I want to connect to the read-write pod. And I'm just going to connect as user Postgres and database Postgres, and should ask me for a password, which if all goes well, I'll just paste, and I should be able to connect. So in this case, you're seeing that I'm able to connect from the outside of the cluster, from inside of the cluster, and so I have a Postgres cluster running with 2 instances, and everything is good so far. For now, we're just gonna delete this pod, because I'm gonna create a much more advanced one. So I can just say delete first the pod, and then the one that I'm using for psql, and then I'm just gonna go on and delete the whole cluster. I can just do this by calling delete on the YAML file, and if everything works, I should get the pods being destroyed, terminating, and we'll have this clean. Now we'll start creating with a more advanced cluster. All right, so let's move on. Let's go to the complete cluster. So first of all, we're just gonna create a specific namespace here. Now so we have one namespace for monitoring, one namespace for Postgres controller, for Postgres controller, the Postgres software itself. And now we're gonna create another namespace for creating the clusters here. The previous cluster, this simple cluster, was created on the default namespace. Now we're gonna create on the namespace, specific namespace called Tema. Of course, this could be used for enforcing permissions, access control, and so on and so forth. Now, before creating this complete cluster, we're gonna follow a set of steps. The first one is gonna be creating an instance profile. An instance profile is a way that we have to try to suggest or enforce best practices in terms of resource utilization. We've worked on environments with hundreds of Postgres clusters where each cluster or each instance is of a different size. This is actually chaotic and it's quite hard to manage. It's better to try to standardize on some instance sizes. And this is exactly what an instance profile is. So an instance profile is another CRD, another of these custom resource definitions, custom objects that we have created in Postgres. That is basically to associate a name with resources for an instance, being resources basically CPU, cores, and RAM. So by giving it a name, you can just reference this name later on and say, I want to create a cluster of size small or large or 2 extra large or whatever you want to call those names. And therefore, you can standardize on this best practice and have more uniform sets of instance sizes. And of course, you could even enforce permissions on this such that users may, or of a certain level, may not be able to create new instance profiles, but may be able to create clusters that reference to these instance profiles, therefore effectively enforcing these best practices. So creating an instance profile is pretty simple. It's a YAML file that looks like this. So let's create this instance profile as a YAML file here, my local file system. Again, I hope you're, if you have a Kubernetes environment, you can also be running this alongside with me. I create the YAML file, so let's just apply it. Pretty simple, and I'll have the instance profile created. This doesn't create any physical resource, it's just metadata, but we'll see how it is used later. So far, so good. Excellent. Of course, we can create, this is called size small, right? And it says CPU cores and 8 GB of RAM, but I could create many sizes, many profiles if I want. For now, this is good enough. Let's move to the next step. And this was one of the questions that we had before, how to tune Postgres. So Postgres, we could have said, you know, like this is very typical in Kubernetes land, create a config map. Config map is kind of some metadata that can be accessed and put whatever there, put actually a postgresql.conf file there, and we'll just copy and paste it into the container. But in Postgres, we want to make sure that users that are not that experts do not have a hard time to mess up with the system, right? What if you put there a wrong file or invalid parameters or with syntax errors? We don't want to do that. We want to enforce a stronger validation. So we have created our own CRD for the Postgres configuration called sg-postgres-config. And so it's another YAML file where you specify the parameters. The main difference is that these parameters are strongly validated before being created. So when you create the CRD, the parameters, their values, and the version checking is going to take place. So if you use a parameter invalid for this version, it's going to be rejected. If you select a wrong value of wrong type, it's going to be rejected. If some value is out of bounds, it's going to be rejected. So this way we enforce also a correctness on the Postgres parameters. But also, as we shall see right now, you can tune some parameters, but by default, we are also tuning a lot of those. Obviously, your parameters take precedence. But once you create a Postgres sg-postgres-config CRD, you may query it later and see also which parameters we tune by default for you. So procedure is as simple as it gets. Let's just create yet another YAML file. Which is, we're going to call it this way, with this content. Yep, the content is pretty simple. I am using always the namespace demo. I'm using this name for the configuration. And then I specify a Postgres major version. As you know, major versions are, any minor version will apply. So I just need to specify the major version to which this configuration is going to be valid. And then the parameters as they appear in a PostgreSQL configuration file, except that, as I said, they're strongly validated. And then apply as usual. So let's just go and apply this. I just say kubectl apply, just f this file, and this is also meta information, doesn't create anything other than the validation, and I'll get this. Now, what is interesting is that after being created, I can call the scribe on the generated CRD, and I'll just pipe this to less. So sorry about that. So I'll be able to see what parameters, this is a describe command where we'll see what we just created, and we'll see all the parameters that in reality this configuration has set, which includes the ones that I set by myself, plus some other parameters that we inject by default. As you can see, we have tuned quite a few parameters here. And to make it even more clear, on the status field, we specify which parameters we specifically tune, not the values, but just the names, so you understand which parameters come from our default tuning, which comes from your own settings. But obviously, you can override all the parameters that we are setting with default values, except a few that are blacklisted because they will compromise the stability of the cluster. But there are a few, obviously. So, good enough. We have created with this an instance profile, which we'll use. We gave this instance profile a name. Now we have created a Postgres configuration with a name. We can also do the same with the connection pooling. If you remember, Postgres will include connection pooling by default. You can disable it if you want. Just set this property, the SG cluster pods disable connection pooling if you don't want it. But otherwise, it will come with a connection pooler in front of Postgres on the same pod. Now, it also comes with a default configuration that you can also tune, but it's tuned by default. Now, if you want to create your own custom configuration, the procedure, as you can imagine, is pretty much the same. This is yet another CRD called SG pooling config. And let's just create this YAML file. We're using PG Bouncer as a connection pooler mechanism. This might be changed in the future, but this is what we have right now. And you can set and override pgbouncer.ini parameters. So let's just generate also this file. Copy the contents and kubectl apply that file. Again, this is only metadata, so this is not going to generate any resource. And we can also describe this this file to see which parameters are tuned by default. I'm just going to move along, but you can see here it's on the tutorial. You can see the result. Good. Now, we're going to create a cluster, and we're going to see, hey, I want to use this instance profile for this cluster. I want to use this Postgres configuration for this cluster. I want to use this connection pooling for this cluster. But I also want to have automatic backups. To have automatic backups, I need to create what's called a backup configuration, which is yet another CRD that represents how to take backups. And within these backups, I need to specify the credentials to access the bucket, in this case, the S3 bucket. Could be any other object storage. In order to specify the credentials, we use usual Kubernetes practice, which is to reference a secret. Secret is a Kubernetes object where you may store information which could be confidential, such as credentials. So what I'm going to do is I'm going to create first a secret, the standard Kubernetes object, and then I will create a backup config that will point to this secret to fetch the credentials from there, and that will be the backup config. So let's go into backup configuration, and from here, let's specifically look at about how to create a specific secret for accessing an S3 bucket from Amazon. The secret, again, is a standard Kubernetes object, and the YAML file I need to create is going to look pretty much like this. However, and in order to save copying and pasting here confidential credentials that I just generated, if you remember on the previous step as part of the prerequisites, I generated the credentials on a JSON file that is stored on my file system. And I just have a handy script here that is gonna basically extract the same, the credentials from this file and create from the command line a secret equivalent to this. So you can either just copy this and create a secret and you do kubectl apply and just copy and paste here the correct values. But what I'm going to do here is use this script, which is more convenient, and especially because I'm sharing the screen in order not to be able to show what I shouldn't. So no, I'm not going to cut that. I'm just going to make sure that this file is here. So this is the file that I generated, just to make sure it was generated a few moments ago, correct? So let me just paste this command. It's going to be very convenient here, and credentials file is going to be this .tmp creds.json, and if all goes well, I should get the perfect, the credentials file, the secret generated. So now that I have the secret generated, I can generate the backup config. Excellent. If you don't want to do it this way, just create this YAML file and do kubectl apply, and you should get the same result. So how does a backup config looks like? So the backup config is yet another CRD. As you see the pattern, we create a CRD to represent any concept that we may abstract away. And we assign it a name and then some parameters. What are these parameters? So first of all, the most important thing is this cron schedule, which specifies at which periods I want backups to be taken, base backups. In this case, because this is a demo, I want to have backups taken every 5 minutes. So I'll have time to show you maybe that one backup is created. The retention window, how many base backups I will keep, and in between there will be WAL files. And what is the storage type? In this case, I'm going to set it to S3 because I'm using an S3 bucket. And here I specify the parameters for the bucket. It's going to be the bucket name, which I'll need to specify. And this is the credentials that basically refer to the to the secret that I just created, which is should be called the same way: S3 bucket backup secret, S3 backup secret. Yes. And this is a secret key selector, which is a standard Kubernetes pattern. It's called a secret key selector, where I specify the access key ID and the secret access key, where the name is the name of the secret and the key is the key that I want to access within that secret. So let's just copy this file. First, I'm giving it a name, so let's just add to this file with this content. And let's edit this to set up the bucket name. And the bucket name is, I don't remember, it was S3. Yeah, previous command. Oh, it's probably this variable. This is exactly what I want. So I'm on the same session. That should come quite handy. There we go. I just want to make sure that I use obviously the same backup name, bucket name, right? Otherwise, I won't be able to send the backups here. All right. So I think we have this file ready. And so how to use it? Just the usual apply, just F, S3 backup config. And again, it's only metadata. It will create a backup configuration. All right. We're not there yet. We just need one step more, which is to create a distributed log server. If you remember from my previous presentation, I was explaining that we have created a mechanism to ship the logs to a remote location from all the pods, potentially of many clusters. And this remote location is going to be yet another Postgres database with timescale extension installed for handling very large volumes of incoming logs. And guess what? This is exposed as yet another CRD. Behind the scenes, you don't need to worry, well, where's FluentBeat, where's FluentD, where's this Postgres, how to install timescale. Everything is handled for you. Just create a distributed log server. Remember that a distributed the logs for all the pods for one or more clusters. And so it's a dependency. We're going to create first a distributed log server, and then we're going to create a cluster that will say send the logs to this distributed log server. Yet another CRD, it's called S3 distributed logs. Pretty simple in this case. We're not messing here with the retention policy of the logs, but we can do that. You can go to the documentation here and check all the parameters. But for now, let's just create this YAML file. So paste this here and the content. And let's create this. Oh, sorry. F. In this case, this is going to create resources because this is a Postgres instance with a FluentD container and with an API service. So because we're operating on the demo namespace, we should soon see here the distributed log servers being created. This name distributed logs is exactly what I specified here is the name. And in a few seconds, we'll get the distributed log server being created. Excellent. Once this is created, I'm finally going to be able to create my Postgres cluster, right? In this case, let's recap briefly what we have done so far. We have first, we created a simple cluster and see how we can connect to it from inside the cluster, which should not be the usual way to connect to it, or how to connect via the service. Or connecting via the service, we gather the generated password for the super user, and then we created another pod with a tool called pSQL, so to be able to connect, and then we pointed the host to the DNS service, which is exposed as a cluster name -primary. And specify this password, and we're able to connect. Then we destroy this cluster because we want to create a more advanced one. This is more advanced in the sense that we are explicitly specifying an instance profile, so we have tight control over the CPU and RAM resources that this cluster is going to be using. We have created a customized Postgres configuration, so we can use this Postgres configuration. We have customized a connection pooling configuration. We have created the secret, which was a prerequisite for creating a backup configuration. So this cluster will also have backup, automatic backups. And we have also created, it should be created already by now, exactly, distributed log server, which will be able to collect their logs from all the pods from this cluster that we'll be creating. By the way, I'm doing this all from the command line. I shall remind you that you can also go back to the web UI and check everything also. In this case, we're operating on the demo namespace. So let's go to the demo namespace. And here we can see, for example, there's no clusters yet, but there's an instance profile. This size is small, if you remember, with 4 cores and 8 gigabytes of RAM. I can create a new one from here if I wanted. Actually, something I can do. Let's create size medium, for example, with, for example, 16 gigabytes of RAM and 8 cores. And here we have another profile, and I could have checked this also from the command line. For example, I could do, you could tell demo get SD instance profiles, or see. I can also use a shorter version if you prefer, and it will show all the instance profiles that I have created, right? This one I created 15 minutes ago, this one I just created from the web UI. This is what I wanted to show, that everything that you do from the web UI, you can check from the command line and vice versa, because it all goes back to a CRD. From the web UI, we check the CRDs, from the web console, we query and we create the CRDs. So here we can see everything that we're doing, the Postgres configuration that we created. Also here, it's very interesting. Here, I maybe need to make the font size a bit smaller, but it's a little bit more clear which are the parameters that I set directly and the parameters that have default configurations. I also have here some help. For example, if I want to check any parameter, it takes me to this website that I mentioned before, PostgreSQL code.nf, that Anastasia also mentioned, and that it provides a lot of information about configuration parameters. So this the web UI sometimes is also more convenient because it provides you advanced capabilities, like in this case, checking documentation of some parameters. The same with connection pooling, where I have, this is the default parameters and the parameters that I set, and the backup configuration. Here I can see that the backup configuration is pointing to an S3 bucket called like this, with the credentials, which I cannot see for obvious reasons, and all the capabilities here. There's always hints to help you on different properties, etc. And we should have also the distributed log server. Excellent. I think we're ready to create the cluster. So let's go ahead and create this more complete cluster. Yours is not that much hard. It's going to be an S3 cluster, as we did before. Let me just copy this and start running it. It won't take much, but I prefer to run this command as early as possible. So let's create this file, and I'll explain what it is later, or what are the differences with the one that we created before. Okay, and while this creates, I'm just going to set a watcher here. Demo get pods. Okay, so here I see the cluster being created. This is normal, by the way, don't get scared. This message is normally very scary. Because we're adding a new cluster that's going to ship logs to the distributed log server, it's restarting. This is the consequence of a restart of one of the containers. It will be restarted in a few seconds. But this entails no data. Here you see it's already restored. But this entails no log loss. If you remember, there's buffering on the pod. So while this container is restarting, the logs are not being sent to it, but they're not lost. They're still on the original source of the pods. If they were, in this case, of the clusters trying to send logs, it will buffer them for a little bit until this container is restarted. This is a limitation of fluentd. We're hoping for a future version of fluentd which allows a reshuffle of the configuration without restart, but for now we need to restart it. But as you see, it doesn't really have any effect in practice. And here we're seeing already the second instance being brought up. Again, we can also check this from the, here we also see, yes, cluster appears here, and we see the cluster creation here. Where you have cluster 0, the pod name is already active. Cluster 1 is being fired right now. And this is the primary. Excellent. So it all looks pretty good. This cluster contains 3 instances. So the second one is creating right now. So let me go back and explain what was the difference with this YAML file. Still short YAML file, right? There's nothing super special. The difference are that I'm using a specific namespace. I also hard-coded specific major and minor version of Postgres. This definitely can do. The instances, the instance profile, I'm explicitly specifying which instance profile I want to use. Size, I'm just giving it a little bit more size here. And here, under configurations, is where I'm using the references to the names of the configurations that I want to apply. You can think of this as foreign keys, right? So this is a foreign key to the Postgres configuration. This is a foreign key to the connection pooling configuration. This is a foreign key to the backup configuration. And also, I want to say, send the logs to this distributed location, which is the distributed logs. Finally, I want to enable the connection to Prometheus so that I will get monitoring information from this cluster on Prometheus. And that's it. The cluster, it's running already. Looks good. I should be able to connect the same way as I did before. For example, like this. In this case, not simple 0, it's cluster 0. And I shall see, yes, because I'm not in the right namespace. I shall see now a connection to Postgres, so I have a Postgres cluster. Let's, by the way, I didn't do this before. Let's demonstrate that there is some replication going on. So let's create a database demo also. It doesn't exist, just to double check. There's no tricks here. It doesn't exist a demo database. Let's create a database demo. And let's connect to one of the replicas, for example, and see that that database exists. Cool. So there's Postgres, it's replicating. If you're low-level user, you may also want to check, for example, connect to the Patroni cluster and issue a command like patroni ctl list to show what is the status of the cluster from the Patroni perspective, right? Yeah, so here we have, and here we see there's 3 nodes. Well, this is the leader node, and so forth. Cool, excellent. Let's go back briefly to the web UI. Effectively, we have the cluster here, and let's look at what we integrated into this web console. So first, we have the configuration. Configuration is just a view of this YAML file, nothing special, but I have here a link, so I can go to the instance profile or to the configuration, etc. Right? Then we have the backups. The backups, oh, good. Because I said to 5 minutes, we have already 1 backup created from the cluster. Next 5 minutes, I'll have obviously another backup here created. Here, see some details about the backup, the size. Obviously, there's almost nothing. Compressed is even less. This is the name of this backup. And I can also, this one it was taken, I can also click on any backup and find little information about this backup, right? What is the size, the Postgres major version, the name of the backup itself, where it came from, the name of the cluster, when it was started, the LSNs, when at which point from the Postgres streaming process, the basically representation of the last sequence number in Postgres started and when it finished, a specific UID to globally identify this backup, specifically which pod it was created, which was the master pod at the time, timeline in which it is, the internal Postgres identifier, etc., etc. So we have here a wealth of information coming, even the full control data that came from the backup location. All this is provided automatically for you on the web UI. You can also check the same information from the command line. As I said, everything you can do on the web UI, you can do on the web command line, because backups, guess it, they're just another CRD. So from the web, from the command line, you can also go and check the backups because they're just another object that we create on Kubernetes. The logs. So I mentioned that we use this technology to ship the logs to a central location, and here you can see the logs. In this case, here we have the logs coming from all the pods together on this web interface, right? I can use this to filter, for example, let's say I want to filter only Postgres logs coming from the pod name called cluster cluster 0, for example. And I have here the logs. And I can also click on any log, let's say this one, and I'll see all the detailed information about this specific log. Depending on the command, of course, you may have more or less information here, but here we have all the information about this specific log from this specific pod, in this case from Postgres. And this right now supports Postgres and Patroni. If I clear the filter also, or just select Patroni, we may also see information from Patroni. For example, information, he's the leader. So yes, we know that cluster 0 is the leader. And we have this information coming from Patroni here. And we can click, as I said, on any log to get more information about them. We can also do full text search on these logs. And this is going behind the scenes to a Postgres database, right? So you can also connect via pSQL and execute SQL commands. And last but not least, we also have, if everything worked well, this embedded Grafana dashboard. So I could select a cluster here. By default, it will select the cluster 0, and this will load Grafana. And as you can see, this is embedded into our web console, and it will show all the dashboards that we have created by default. Taking a little bit to load, but it should come soon, or not. Interesting. Ah, there we go. I don't know why it's so slow. Maybe it was the first load. Okay, anyway, by the way, I'm pulling this cluster is right now running on US system. I'm in Europe, but yeah, okay, here we have it. So here we can see all the specific dashboards that we have created. Of course, this is not very active cluster, so maybe we don't have a lot of information here. Let's actually look, for example, at the database size, where we should have some information already. You see the database demo here, Postgres database, some counters here, the biggest tables. Well, of course, this information on this specific case right now is not super interesting because there's no activity on this cluster. But as you can see, we have created specific dashboards to deal with load, usage information, transactions, for example. These two come from Envoy. Remember that we were exporting specific metrics from Envoy. This comes from Envoy. They're not hitting Postgres. Obviously, general information about the database, etc. So we have all this monitoring information embedded into the web UI. This is one of the advantages of using the web UI. And just think about this. What have we done to create all this? Automatic backups, which probably we should have already. Yes, a second backup already generated. Distributed logs, embedded monitoring, and creating a Postgres cluster with connection pooling, with high availability. For example, I can demonstrate that if we have these 3 pods, I can obviously just kill one. For example, let's say delete pod cluster 0, and the cluster will reheal very soon, and will elect either cluster 1 or 2 as a new primary. We can see here this, for example, from here, and it will find one. You see that right now this is pending and already elected cluster 1 as primary. And if we were an application connected to the primary, it will see a small downtime, and then it will again reconnect to this cluster, but now we'll connect to cluster 1, which is now the new primary. And this one, by the way, is being redone again. So you've seen that in a few seconds, after killing a whole server, a pod in Kubernetes, another pod was automatically launched because we're using, in this case, external disk. The disk is just reattached. So this is a very fast process. And we have the cluster rehealed. Of course, it will be different if we need to schedule a physical node, but for the most part, Kubernetes takes parts of this. And now we have cluster 1 as a primary node. And so from the user perspective, it was a very simple operation. So that's all that I wanted to mention today about the tutorial. I would like to insist that you can just go to stackers.io, documentation, and then tutorial, and just reproduce, 3.3 tutorial, and just reproduce the very same steps that I performed today in order to come to the same results. If you're doing this on Amazon AWS, it will be straightforward. If you're using a different Kubernetes environment, you should also have no problem. There's minor tweaks for all the Kubernetes environments, which are also documented in our documentation under production installation. But if anything happens, please feel free to join us on our Slack or Discord groups. They are on the main webpage linked from there, and you can just reach to us. So I really encourage you to try this out, and I'm open. I think we have some minutes left. I'm open to questions.
Your talk, and
Pleasure.
yeah, and I congratulate you that everything went smooth, and it seems that everything really works well, which is great for masterclass and even greater for the system. So we have now only one question in the chat, which is about limits and requests for pods, whether they were set or not.
Yeah, it's a very good question. So as I mentioned, Postgres is a quite opinionated framework, right? The team behind the teams, I would say, behind Postgres, they include the developers writing the code, and they include the DBAs writing the specs on how things should be done. And one of the goals that we have from our DBA team is to enforce best practices. One best practices when running a Postgres production database is that you have strict control of your resources, which in Kubernetes land means to specify both the limits and the requests and make them the same. So we're doing limits equals request equals the instance profile that you set. So this is good for production environments. This may not be ideal for development environments where you want to do a little bit more consolidation of resources. So there's actually an open issue for us to let you specify different values for the limits and the requests. But again, this is only applicable for development purposes where you want to consolidate more resources. For production workloads, we absolutely discourage that option because it may make, for example, the OOM killer to fire when you cannot really strongly control it. We also recommend as a best practice, and this is enforced by default, that you run no more than one Postgres pod per Kubernetes node. We use an anti-affinity rule set by default to prevent this. You can override this. You can set up what is called a non-production option, which is to override the anti-affinity condition. If you want to run several pods on the same node. But other than that, we enforce this. So we're trying to enforce best practices all across the board.
Yeah, thank you. That sounds wise. And yep, that's it. I think there are no more questions in the chat. Maybe we'll wait a couple minutes more, and then you can follow to special chat where maybe people will ask some more questions. And yep, thank you.
Excellent.
My compliments to the dashboards and the web UI, which is quite clear to follow. Even when I see it the first time, it looks really easy to follow what you do. So yeah, that looks really good.
Thank you. Thank you very much. I appreciate it. And there's been a great effort also on the web UI, and there's even more things coming to the web UI that I believe will be quite interesting. One of our goals, as I mentioned, is to make Postgres really accessible for non-Postgres experts. We want to make Postgres a universal database so that anyone that at least knows the basics of Kubernetes administration will be able to use Postgres, which is, as you know, hard for production environments.
Yeah, I see. So I think that we're right on time. And thank you once again. So I want to remind our listeners that they can vote for the talk and masterclass. And yeah, now you can follow to a special chat and talk to speaker. Thank you.
Okay, I'll go there. Thank you, everybody. I'll appreciate your feedback about the session, and see you in the room, speaker room.